This is Mrs. O'Neill for AP Chemistry, Chapter 4, Section 1, Aqueous Reactions and Solution Stoichiometry. Again, look at those terms on page 149. Make sure you understand them. Water covers nearly 2/3 of our planet, and this simple substance has been the key to much of Earth's evolutionary history. Life almost certainly originated in water, and the need for water by all forms of life has helped determine diverse biological structures. And I want to remind you, substance can either be an element or a compound. So in section 1, we're going to talk about the general properties of aqueous solutions, and you should be able to determine whether a substance will dissolve as an ion, a molecule, or a mixture of the two when you put it into water. So a solution. And I want to remind you to pause the video, fill in the blanks, and then play to hear my words. So a solution is also considered a homogeneous mixture. It has two parts, the solvent, which is the dissolver like water, and the solute, which does the which is being dissolved like the salt. And here's your example down here. Hopefully you get that. So electrolytic properties. So something is going to be an electrolyte or a non-electrolyte. And an electrolyte means that there's electricity moving, which means if something is moving, ions are moving. And if ions are moving, that means electrons are moving. So usually an ionic compound will break up into ions. And so we have these ions, and these ions mean that electrons are being transferred, and that's considered an electrolyte. Something that does not dissociate when it goes into water, does not break into ions, would be something like a covalent compound, like your sugar. So we're going to see the difference between salt and sugar. But first, I want you to figure it out. So take a moment, pause the video, draw what you feel NaCl would look like as a solid, and what NaCl would look as an aqueous solution. That's what the AQ stands for. And you're going to do the same thing here with sugar. So take a molecule of sugar. What does it look like as a solid? Take a molecule of sugar, and what does it look like when you dissolve it into water? So again, pause the video, take a moment to draw it on the molecular level, and then play to hear my words. So here's your salt crystal, and here's your salt water. On a molecular level, it looks like this. It looks like you have your positive and negatives, and they're all scrunched together because they're all attracted to each other. But in water, your negative is going to be surrounded by those positive water molecules. Hopefully, you drew those H2O molecules, and you have that attraction here. Same thing with the positive sodium ion. You're going to have the negative part of your water molecule, remember, because this is polar. So you have the negative part of your water molecule attracted to the positive ion of the Na. And remember that this is called an ion dipole intermolecular forces, and we're going to talk about that again in later chapters. So if you look at sugar, again, here's a cube of sugar and sugar into water dissolving. But on a molecular level, here's our water molecules. Again, not too worried about that. But notice that your sugar as a solid stays a sugar as a molecule when it's dissolved in water. Those sugar molecules did not break apart into ions. They stay as one molecule, stay as one entity. And this is one of the reasons why it's going to be considered a non-electrolyte. So when we get to class and go over these notes, I'll do a light bulb demonstration so you really truly understand what those ions are doing and how they produce that electricity and moving electrons. So here, how do ionic solids dissolve? Again, on a molecular level, we have NaCl, NaCl, NaCl. Remember that crystalline solid structure? And we're going to have a water molecule break apart that ion because the negative oxygen, partially charged oxygen atom is attracted to that positive sodium. And we'll have another water molecule come in, and that positive H, the partial positive H attraction, is going to be attracted to that negative chloride ion. And here you have what's called hydrogenation. So we have that positive surrounded by the oxygen molecules and a negative surrounded by the hydrogen molecules. And this actually was something on the AP exam just a couple of years ago, so something to keep in mind. And again, I will click here and show you more animation when we're in class, just make sure that we understand this material. So we also want to remember, like I was talking before, these are called ion forces. So these black lines that I drew here between the H and the negative, and these black lines here between the oxygen and the positive, these are considered ion dipole forces, and the Y. So if you want to take a moment to think about that before you see the answer, I suggest you do that. We want to remember that the ion is that charge in the middle, and we want to remember that dipole means that we have a polar molecule, and water is a polar molecule, which means it has partially positive and partially negative, and that's why it's attracted to the negative here, and it's attracted to the positive here. But notice the water molecule stays as a molecule, very similar to the sugar. The sugar stayed as a sugar molecule. Water stays as a water molecule, but the part of its molecule is attracted to the positive ion that is broken apart from that salt. Okay, so again, I bring this up because I believe it's chapter 11. We're going to go in great detail about these ion dipole forces or intermolecular forces. So why do ionic compounds conduct electricity? Again, because of those ions, it's breaking apart, and I will show you this demo when we get to these notes in class. Same thing here. So if we have the sugar in here, again, notice the light bulb does not go on because it is not breaking apart into ions. So we have NaCl breaking apart into ions, Na plus and Cl negative, but here our sugar really just stays as a sugar molecule, so there's not going to be any electricity, no electrons are being moved around. So give it some thought. Again, pause the video. What dissolved species are present in a solution of KCl? How is this going to break apart into ions? Hopefully you guessed K plus. And now we're going to add that AQ for aqueous and Cl minus, again, AQ for aqueous. On B, it's going to be the Na plus, AQ for aqueous sodium, and we have the ClO4, which is perchlorate aqueous solution. Oh, by the way, Cn is cyanide and K is potassium. So there are three types of solutions. Things that are going to be considered a strong electrolyte, that totally breaks up into ions. You have a weak electrolyte that breaks up into ions, but also some stay as a whole, and we're going to talk about that in just a slide or two, and non-electrolytes like your sugar. So a strong electrolyte is your salt, a non-electrolyte is your sugar. Then what are these weak electrolytes? Well, when we get to the acids and base chapter, you're going to know that there are some acids that are considered strong because they completely dissociate, and some acids are considered weak because they partially dissociate. They break into ions, but some also stay as a molecule. So if we recap, strong electrolytes, you have your AB compound, totally breaks apart. Weak electrolytes break apart into ions, but notice the difference in arrows. The straight arrow is considered completely going to dissociate, but this is what we call an equilibrium arrow, which means yes, the AB compound is going to break into ions, but at some point these ions are going to be attracted to each other and go back and form some compounds. So if you have a strong electrolyte in solution, all you have are the ions. If you have a weak electrolyte in solution, you have the compound and its ions. You have all three of these components in your solution. So again, strong, light, very bright. Weak, you're going to see a light bulb go off, but not as strong, on a dim level. And a non-electrolyte, there's not going to be any light bulb going off at all. So again, you want to notice that what's considered strong electrolyte, what's weak electrolyte, what's non-electrolyte. What you really need to know at this point is, your strong acids and strong bases. Yes, you do need to memorize these. Yes, we're going to talk about this. Yes, and yes. So you might want to, again, pause the video and make yourself a list. So how can we memorize these? Well, if you look at the area over here, oh, I'm sorry, do the acids first. If we look at the area over here, here are your three main acids, hydrochloric, hydrobromic, and hydroiodic. So these are your three main acids here besides the ones on the bottom. So those three you can find easily on the periodic table. These you're going to just have to memorize. Strong bases, on the other hand, if you notice, it's lithium through cesium, calcium through barium, and they're all end in hydroxide. So somebody said that looks like a B. So to know that the bases are here on the left and the acids are here on the right of the periodic table. So again, pause the video. I did name some of them, but then check your answer. Hopefully you got them right. If you have questions, hopefully you will ask me, or you will go back and look at your acids and bases naming in one of your previous sections. So what can be strong again? Any ionic compound is going to be strong. It's going to break up into ions. Acids and bases on the list are going to break up into ions. And any compound starting with NH4, we're going to consider that an ionic compound. So that will also be strong. What's going to be weak? Anything that's not on that list. Acids and bases. If it's not on the list, it is weak. And a non-electrolyte are going to be your covalent compounds. So again, give it some thought. Hopefully you chose NaOH. It is a strong electrolyte. It is a strong base, so it will dissociate completely into ions. And what are the two ions it would break into? Sodium plus and OH minus, or hydroxide minus 1. So again, pause the video, do your practice problems. Hopefully you'll understand the information. Hopefully you'll get your answers correct. And if not, again, when we go over this in class, I will answer any questions. And yes, you need to memorize the list. So if the acid is not on this list, it is weak. If there's a base that's not on this list, it is weak. So it's a lot easier to memorize your strong acids and your strong bases because there's not many of those, but there's so many weak acids out there. So we want to memorize the strong, the few strong, and use your periodic table to help you. Okay, again, your periodic table, the B's are on this side for base. And all you have to do is add OH to them, and these are metals. That's another thing that's going to be important later. Your metallics combine with, excuse me, hydroxide to form that base, and then you have your acids here, and these are nonmetals. So again, those are going to be important later on. Okay, see you in class.